Welcome to the inaugural screencast of CS311 operating systems. Boy, am I nervous. Makeup! How do you turn this thing off? This screencast covers Chapter 1, Sections 1, 2, 4, and 5. This simply summarizes the material covered in Chapter 1, all of the material. This gives the chapter objectives. This is what we'll be focusing on mastering in this chapter. This is the view of the operating system from the user. To the user, the operating system abstracts the base hardware of the computer and makes the computer much easier to use. Imagine what using a computer would be like if you didn't have an operating system. This makes explicit the layering and abstraction provided within computing systems, right? Remember, layering and abstraction are fundamental CS principles. So from the bottom, we have the hardware. On top of that, the operating system. On top of that, application programs, including such things as compilers. And finally, at the top, users. This is simply another view of that layering and abstraction. This gets at operating system design goals. Ease of use for users, good performance for both users and from the system perspective, and efficient resource utilization, which I think is important to both users and from the system perspective, but perhaps more so from the system perspective, especially traditionally with shared mainframe and mini computer systems. We also see that the design principles differ based upon the type of the system, whether we're talking about a mainframe or a workstation for a single user, or a mobile device, or even embedded systems that often will have operating systems. This slide shows the systems perspective of an operating system as a control program that controls processes, which are running programs, to prevent errors within the system or improper use of the system. Errors are such things that divide by zero. Improper use are such things as segment violations, a process trying to read the memory of another process. Also, the operating system, from a system perspective, is a resource allocator. It has to allocate among all the running processes the finite resources of CPU cycles, memory, and by memory I mean RAM, and also arbitrate accesses to all of the I/O devices in the system. The one thing I want to focus upon in this slide is that third bullet. The one program running at all times in the computer is the kernel. I think it's debatable about whether the kernel itself is a running program. I'd say the best view, or not the best view, but the way I look at the kernel is it's similar to a library, right? It's code that is invoked by a user process. There's some differences between traditional libraries and the kernel library, if you will, that we'll get at in subsequent slides. We'll cover the boot process later, so I'm going to skip over this slide for now. Here's a review of what a computer system is. We have the CPU on the left, memory, i.e. RAM, at the bottom, and then everything else is I/O devices. This slide is pointing out how much concurrency or parallelism we have within our computing system. But the operating system has to manage all of this concurrency, all of these devices, sometimes with just a single CPU. And by single CPU, I mean a single core. Fortunately, CPUs are much faster than I/O devices, generally speaking. Devices signal the operating system that they need attention via interrupts. So imagine a disk drive that just completed a read operation. But it would inform the operating system of that by sending an interrupt to the CPU. The CPU would pass that up to the operating system, and then the operating system would perform whatever management tasks were necessary to complete that read operation. So the kernel is passive, right? It awaits interrupts from devices or system calls from user processes. I'll skip this for now. We'll come back to this later in the semester when we look at device handling. All right, so let's briefly walk through an interrupt. So imagine user process A running along, and then it wants to read data from a file. Right, that translates at the bottom to disk read. So this user process executes a system call for the disk read. That is passed on to the operating system. The operating system constructs a command for that disk drive to perform the read. That's taking place here. At the same time, that user process A, can no longer run, right? It's blocked until the file data is ready. So what happens at that point is the operating system will suspend that process and then look for another process to run. Let's call that process B, and to keep things simple, we'll assume that process B is the only other process available to run, and it's not doing I/O, so it'll just run and run and run. At some later time, the disk drive will have completed the read, so it interrupts the CPU. The CPU passes that interrupt up to the operating system. The operating system ceases executing process B and completes the transfer, the disk transfer, making that data available to process A. And then at that point, process A will no longer be suspended. And then CPU scheduling algorithms come into play because we have a decision to make: continue running process B or perform a context switch and begin running process A again. Okay, so on this slide, the thing to focus upon is this system call, right? That's the call mechanism by which the operating system library is invoked from a user process. As we'll see later, the system call is an instruction that invokes, in essence, a function call, but also has a side effect of increasing the privilege level of the running program. We'll see this later, but the CPU will make a transition from what's known as user mode to kernel mode. We'll talk about that a little bit later. You can review this material on your own. The most important thing here is that some memory is volatile and other memory is non-volatile. Layers in the memory hierarchy are distinguished by speed, registers fast, disk slow, cost, a register bit is expensive, a bit on disk is inexpensive, and volatility. Data on disks survives power events. Data in memory and registers generally does not survive power events. For your review, this is simply a diagram showing the various layers of the memory hierarchy. Right, so you may be familiar with caches that exist between RAM and registers in the CPU, but caching is a technique that is used more generally. Think of virtual memory. And also the file system at the block level will cache disk blocks. We'll skip this for now. This is CS220 review. I'm going to skip this. We can skip this and skip this. Skip. Skip. Skip this too. I must be sounding like a broken record by now. Multiprogramming is the technique of switching control of the system from one process to another to increase efficiency traditionally. Batch systems were not interactive. You submitted a job and came back an hour or a day later to pick up your results. Time sharing is a technique that time sharing systems allow interaction between users and the operating system. That's what we're using if we're all logged into Phoenix at the same time. In a sense, the main distinction between a batch system and a time-sharing system is how much time a process is allowed to have control of the system before a timer interrupts the operating system and the operating system switches to another process. In a time-sharing system, that period of time, which is called a quantum, is kept low so that it appears to all the users that they are the only ones on the system. In a batch system, that quantum is longer, and it's longer in a batch system because each context switch is overhead. In a sense, the system isn't performing useful work, where we define useful work to be executing user programs. So in a batch system, quantums are longer to make better use of the CPU. In time-sharing systems, the quantum is kept shorter just to provide the illusion to all the users that they're the only ones using the system. We'll skip this for now. I will cover this more carefully. We'll actually cover it when we get to memory management. This simply reprises what we've talked about already, so I don't have anything more to say about this. All right, so this speaks to the dual mode operation of the CPU. In kernel mode, all of the CPU's instructions are available, all of memory is available, and all of the I/O address space is available. So in other words, when the CPU is in kernel mode, anything can happen. For that reason, anything can happen. It's not a good idea to allow user processes to run arbitrary code in kernel mode. That would allow any user process to halt the system, to look at other processes' memory or other users' files. Of course, the dilemma here is then how a user process can access a disk or memory at all. And the solution to this is the syscall mechanism. When the syscall instruction is executed, remember the CPU makes the transition to kernel mode, and that opens everything up. But the syscall instruction itself results in a trap to the syscall handler of the operating system, which, being provided by the operating system, right, is carefully crafted code that prevents, if it's written correctly, a user process from being able to do arbitrary things in kernel mode. So the kernel code runs in kernel mode so that it can do everything. And then when control is passed back to user code, the return instruction that is executed has the side effect of transitioning the CPU back to user mode. All right, so this illustrates the process. We have a user process running along. It wants to do, let's say it wants to do a disk read, right? So it informs the operating system of that via a system call. That system call transitions the CPU into kernel mode. The syscall handler is executed. It sees that the user wants to perform a disk read. It reads parameters, sets up a read, and then eventually that return there is most likely, as we talked about before, going to be a return to some other user process. But when control is passed to that user process, the CPU is transitioned back to user mode. All right, so that completes our first screencast. Any questions? No? All right, great.